Thanks, Cindy, for the introduction. Thanks all for coming. I'm very honored to be here. So today I'm going to talk about human-robot collaboration, and in particular, one of the attributes that is a necessary condition for humans and robots to work not just for each other, but actually with each other, is communication. So when you're doing a task with a human partner, you naturally communicate things. And you're communicating them not only through the words that you say and the gestures, but also through your choice of actions. So if you want to break that down, we think about communication frequently as being explicit, right? Speech, gesture. Those are fairly unambiguous. They can be interpreted in any context. But if you go beneath the surface, we have what we think of as implicit communication. So this would be any communication where the context is necessary in order to properly understand it. So a lot of other kinds of gestures, as well as nonverbal behaviors like eye gaze and body posture. We're used to reading these in people and understanding their meaning. But there's an even deeper category of communication, which is functional actions. The manner in which we do functional actions can communicate a lot. So the way that I lift an object tells you whether it's heavy or light, for example. And you take that for granted, you almost don't even think of that as communication, but it is. And if you think about the job of a mime is constructing a fantasy reality and communicating his fantasy to you strictly through the manner in which he pantomimes actions, right? So that is clearly a communicative act. And this is something that we want robots to understand because human partners expect it. And I hope to convince you that that is both necessary and possible by the end of today. So I'm going to give a few examples, a little bit more grounded, just to get you thinking about what we're talking about. The first one is more explicit communication. So we're going to be talking about that whole stack from explicit all the way down to functional actions. But here's an explicit one. So Anne walks into a store and our shopkeeper, Bill, is there. And Anne asks, do you sell Coca-Cola? And Bill says, I sell Pepsi, right? So saying I sell Pepsi is a functional action because it's accomplishing the goal that he believes that she has, which is to buy a brown fizzy soda. But at the same time, there's also this implicature, right? There's this hidden other statement that's buried within Bill's statement, which is the one that literally answers the question. No, I don't sell Coca-Cola, right? That's not actually contained in his statement, and it's possible that it's false. For example, maybe Pepsi is paying him to sell Pepsis instead. But that's sort of the normal interpretation. That's what we would conclude. And even more to the point, if you ask Anne later, did Bill tell you he doesn't sell Coca-Cola? She would say yes. So there have been studies that showed people actually don't distinguish between what they learned through statements and what they learned through implicature. So we just do this naturally. We cannot help it. We don't always do it intentionally either. So think about the Wizard of Oz, right? Ignore the man behind the curtain. That's a functional action, right? This guy has an agenda, which is to seem big and powerful. And so he's trying to distract attention away from the man behind the curtain. But of course, the implicature here is exactly the opposite, right? There's something interesting behind the curtain. And that's why it's funny in the movie, because he's inadvertently doing exactly the opposite of what he intends when he says it. So these kind of implicit communications happen all the time, also with motion. So imagine somebody in a corridor, they have to pass, which means moving to one side or the other. So the question is the guy in blue there going to pass by moving to his right or his left? So you watch the video and see what you think is going to happen. So my interpretation is that initially they were going to both move to their own right side, and then very abruptly at the last minute, he switched policy and actually decided to move to his left instead. Right? And the reason was the lady in red there. Sort of came into the picture and changed his plan. But regardless, whatever you concluded from that scene, you concluded it through observation, right? Through nonverbal behaviors. And so a lot was communicated about the intentions of the people involved through their motion. You can also combine these. So for example, here's a sort of joint collaboration in my lab. This is my student, Will Thomason. I'm sorry, there's no sound, but he says, Baxter, please hand me the soldering iron. And so Baxter goes to reach for the soldering iron, and then Will stops the robot. He says, it's hot, and he does a gesture, right? And the robot actually halts what he's doing, and then regrasps and picks an appropriate grasp, right? So that seems like a completely ordinary thing, except that this is a robot, and the statement, it's hot, is a lot different than the statement, please add a new constraint to your grasp selection algorithm to avoid the tooltip, right? That's what he meant when he said it's hot. But you can't expect most people to spontaneously come up with add a new constraint. They say things like it's hot, and implicitly what that means is add a new constraint to your grasp selection. So I'm going to tell you today how the robot did that. It actually figured that out for itself based on sort of knowledge it had about the context. So here's the outline for the talk. We're going to start with a communications framework to describe how this all ties together for robotics. I'm going to briefly give you a few necessary conditions, and I'm going to take you on a brief sojourn about actionable information, which is a really important concept when you are collaborating with somebody. You want to convey actionable information to them so they can make good decisions. And we're going to do that using a card game called Hanabi. And then I'm going to talk about robots for the next two sections. So 2 case studies in natural language communication to ask for help when something goes wrong for the robot, and then also in pedestrian navigation, and then a few quick concluding remarks. So let's dive in. So this is a paper that was presented at HRI 2017. The topic of the paper was implicit communication and adjoint action, although actually you can also think about it as being some of that more explicit stuff. So this is my students, Chris Mavrogiannis, Julia Proft, and Claire Liang. And basically what we have here is a human and a robot. They both have private information. So you can think of the big M as a set of facts that each one knows. It may be the case that they have facts in common, but if it's in M private, that means that they don't mutually know that they both know it, right? So it's not common knowledge. There's also shared context. So this is the stuff that they both know that they both know. MPub is the common ground, which strictly speaking is they both know that they both know that they both know ad nauseum. And then we have the set of functional actions. So AF it stands in for the semantics of actions. So if I do this action, it will accomplish this goal, right? So there are many ways of accomplishing many goals, and we'd like to pick appropriate ones in circumstances, but our choice of action, as we know, also conveys information. So we're going to, through careful selection of A, we're going to actually encode actions, if you will, on top of it. Or, I'm sorry, encode information on top of it. And then finally, we have this probability distribution, which we assume that everybody more or less agrees on. Doesn't have to be exactly the same, but the idea is that we have some conception of how likely it is to take action A in context M, right? And we more or less all agree. For example, it would be highly unusual if I were to start like taking off my shoes and clipping my toenails during the middle of this talk. So, you know, that would be included, but with very low probability. Okay, so the implicit communication goes like this. There's some hidden fact M hat that the human wants to convey. And for whatever reason, he wants to do it implicitly on top of an action. So he's going to do some generation process. He's going to project his M hat onto an A hat, an action. He's going to perform his action, which the robot observes. And the robot is going to do the inverse, right? It's going to understand A hat, and it's going to transform it into a fact, and hopefully the same one, right? If all goes well, then they can now conclude that they both have this shared fact, and it becomes part of the context for future interactions. So the main focus of everything I'm going to talk about today is really on these two stages, the generation and the interaction. And I want to show you both abstractly what those look like, and then concretely for a few different domains what those look like as well. So this all goes back to psychology. We're actually leveraging something that humans do innately, which is called teleological reasoning. And that is that we connect the idea of goal and action in our minds Throgan and Srinivasa helpfully gave us names for both of these directions. So if you know the goal that somebody is trying to achieve and you're able to guess what action they take to achieve it, we would describe that action as predictable. If, on the other hand, you observe an action that somebody takes, and from that observation you're able to infer the goal that they have, we would say that's a legible action. And I'm going to come back to their formulation of this later. But for now, I want you to think about this second category, these legible actions, because that's really the crux of how we're going to communicate not only goals, but actually all kinds of information. So this is sort of a very metaphorical view of what's going on here. We have a distribution over a set of actions. We're involved in a joint activity, so we have some idea of what's going on. So that limits the scope of what are the functional actions in this context. But some of these actions are high probability, some of them are low probability. By the way, it could be a discrete or a continuum distribution depending on the circumstance. But most of the time, when we observe our partner doing an action, we expect it to be likely, right? Stands to reason. We call those the predictable actions, right? So if you knew the goal, you expected them to do that particular action. If, on the other hand, you observe somebody doing something improbable, you don't say, oh, that's a fluke, it's just some weird thing that they did. That's what we call the legible actions, actually. So the act of observing this improbable action triggers you to think, why did that happen, right? In particular, it triggers a search for an additional fact that you can add to your context mpub. So the fact is mhat. And if you find it, it explains the choice of that action, because in this new distribution, that is a predictable action to have chosen, right? So this is called abductive reasoning. It's inference to the best explanation. And it's something that everybody in this room does every day. So it's an important skill to have, both for humans and robots.
So,
yeah.
So how come you didn't write the posterior of mhat and think about things in terms of belief states? Are you going to be not thinking probabilistically there, but in A you are?
I did not write that to keep things simple. You're right that there is doubt. And in particular, these distributions are often messy. So there could be distributions over mhat, and you could start reasoning about, well, if he meant this, then that, and so all of that is true. I don't want to cloud the big picture with some of these implementation details, though. But if you want to talk about that offline, I would love to dive in. Okay. So to formalize this just at the really high level, understanding is the act of finding an mhat, which for now we'll treat deterministically. So it's an argmax. And we're searching for the most likely fact given the action we observed as well as the context, right? And we can use Bayes' rule, which we have to do because this is the form that we said that humans sort of have built in the probability of the action given the context. And what Bayes' rule tells us is there's this extra term, this P of M given M pub. And that you can think of that as like a regularizer or preventing conspiracy theories, basically. So that says we can't pick some really bizarre explanation for the action that somebody did. We actually want to pick a likely explanation in context. So on the other side, if you're generating an implicit message to send to somebody, your goal is actually the same. So you're trying to now pick an action, but you're still trying to maximize the probability of the fact mhat, right? But now you get to pick the action. And so Bayes' rule in this case tells us that effectively the action is going to be the one that maximizes the ratio of the action given the hidden fact over the action without that fact. And so that is exactly this rise that we saw before. We want to pick the action that's going to maximize that rise, and that's going to be the clearest, crispest signal. And that actually, I think, gets to Dano's question a little bit, because we don't want to pick the ones that are going to be really ambiguous, right? If somebody is scratching their head over what you meant, then you sent an ambiguous signal, and maybe you could have chosen a better one. So, But the takeaway here is really that both if you're on the understanding side or if you're on the generating side, your goal is the same, which is to maximize the confidence of the observer, right, the understander. You, as a speaker, are not trying to maximize your own confidence. If you were, you would shut up because that's the most confident thing you can say. By the way, I want to be clear. Lots of people have had this idea before me. Lots of people have worked in what I'm calling implicit communication in a ton of different domains. This is only a very thin slice through that. The contribution of this work is really in recognizing that all these people were doing the same thing and in writing the abstract formulation of it. Of course, it's abstract enough to be almost meaningless, so for the rest of the talk, I'm going to be showing you how does it actually look in practice. So a few brief takeaways from this section. First, the transmission of implicit information requires careful action selection with awareness of the context. And your goal is to maximize the confidence of the observer. And that separate models exist in many domains for this thing, right? So necessary conditions. So these are the caveats. You cannot do communication unless the following four things are true. The first one is there has to be more than one way of doing the same functional action, right? If there's only one way of doing a thing, like pushing a button, there's not much information to be conveyed there. Similarly, if there are two ways of doing it, but they're equally likely, that's not very helpful, right? Because it's a coin toss which one you pick. So what we want at a minimum is a situation like this, where choosing a hat now seems legible because there's some surprising reason that you chose that. Number three. So this one says that after observing the action, it has to be clear why you chose that action. So knowing the fact actually explains it, right? So you want to avoid cases like this where the rise is just too small, such that it still would have made more sense to do some other action. Since this is a little more abstract, I found an example in history, which is a classic fail. Does anybody here actually remember this event? Do you remember why? Why did John Hinckley Jr. shoot Reagan?
Jodie Foster.
Right. So specifically, he wanted to impress the actress Jodie Foster, right? And you hear that and you scratch your head like, why is that the obvious action that you would take in order to impress? Well, he was crazy. But the point being, he did not know rule number 3, obviously. So, okay, one more rule. And this one is related to the last one. And it's basically saying that there can't be two equally good explanations, right? You can't find two different facts that both explain the action equally well, because then you don't know which one somebody was trying to convey. And this is, I think, exactly Daniel's point. And if you want to start to reason about this, then yes, you need much more probability. You need belief spaces for the facts. And that gets messy and intractable. So I'm just saying don't do it. Not everybody heeds my advice, however. So this is a gesture that is known throughout the world with many different meanings. So depending on who you are and where you're from, this can mean either that you worship the devil, that you root for a football team in Texas, or that you believe that somebody's spouse is cheating on them. So I'll leave it to you to decide which of those is which ones. But you need to be careful when you use a lot of gestures because they do have different cultural significances and so forth. In fact, I believe there was an incident where George W. Bush's daughter was in Finland and did this sign, and I think they thought she was worshiping the devil there. So this actually happens. Right. So if you follow these things, which is hard, you can successfully do implicit communication, but it's clearly non-trivial, right? It's not always easy to find an action that will actually encode the fact that you want to encode. But consider how often we do it. We're incredibly good at, in a social circumstance, we find a way to explain facts or to interpret them contextually in very subtle and sophisticated ways. And this actually leads us to the next idea, which is actionable information. And we actually chose to study this in the context of a party game called Hanabi. And you might ask, why a party game? Well, if you've been reading the news, deep learning has been making a lot of progress in playing games, right? So we've got AlphaGo, we've got Atari now. We can play almost all Atari games automatically. This is the one nut that so far deep learning has not cracked. So there do not exist good AI solutions for party games. And the reason for this primarily, I think, is this subtle social interaction that goes on in these games. And so that makes this a really ripe field for human-robot interaction to study, because these are exactly the same problems that we're facing there. So we looked at this game, Hanabi. It's actually quite a simple game. If you're playing this game, it's a collaborative game, so you hold your hand backwards, so all of your partners can see it, but you don't directly know what's in your hand. But you can observe your opponent's hand, or rather your partner's hand, and you can see what cards are down on the table. And the goal is to get your partner to play cards down on the table so that you have 1, 2, 3, 4, 5 in each of the 5 colors. And if you do that, you win, right? But there's a very strict language by which you can communicate hints to your partners. So you can tell them about number, or color, rather. So you can say, for example, you have 3 blue cards, or you can tell about number. You have 2 twos. That's all of the information that you're allowed to give about somebody's hand. You can't do both, right? So you ask yourself, well, what strategy should I take here? The obvious thing would be, I want to maximize information. If this hint looks really good because I'm giving you a lot of information about your hand. But it may not be actionable information. In fact, it's almost certainly not, because you're talking about so many hints. It's like 3 people talking at once, right? It's hard to understand and pick it apart. So what you'd like to do instead is give more targeted hints. So here's an example of my student Claire Leong on the right giving a hint to her roommate. She says, this is a blue card, and then her roommate says, okay, I guess I'll play it, right? So had it been the wrong card, they would have gotten a penalty, but it was the right card. So her partner did not know the number. She only knew that it was a blue card, but she inferred that it was the correct number such that it was a playable card, right? And the whole idea here has to do with trust in a team. We assume that you wouldn't be giving me irrelevant information about a card, right? So the only explanation for why this particular hint was chosen is that this is actionable information. So with this basic insight, this actually generalizes into various different contexts within the game. People who are really good can give hints about multiple cards and still convey actionable information about each one, if you know your partner really well. So we decided to look at this game and see what we could learn about implicit communication, or implicature. So I mentioned Claire Leong, and Julia Proft was also on this, as well as my faculty colleague Eric Anderson, who does game design. And by the way, this is new unpublished work, so you're among the first to see this. We had 2 hypotheses going in. We thought that teams would perform better when implicature is leveraged than when it's not. And secondly, that humans find implicature more intuitive, right? So to address the first one, is implicature effective? We just did simulations. We had AIs play against AIs. So our baseline was this entropy one, where we just try to hint about as much information as we can find. And in that case, you have to be conservative. You can't play a card unless you know its full identity. Conversely, with the implicature baseline, you give hints typically about fewer cards, but when you do so, you can infer the hidden missing information. And it turns out that the implicature did much better, about 7 points better on average than the entropy baseline. So it seems that, at least in theory, implicature is actually a much more efficient means of playing this game, of communicating actionable information. But then we looked at the second one. So what do humans think about it? We constructed a web-based version of this game, and we advertised it on Reddit. So we got about 1,000 people to play our game, and about 300 left feedback on the survey. And we would randomly pair them with either an entropy or an implicature AI. And so we thought that, for example, the implicature one would do better, just like it did before. We asked them a bunch of other questions as well. I'm sorry to say that we had a negative result. The entropy and implicature baselines were not significantly different here. I think the explanation for this has to do with adaptation, which is that people coming in don't understand the strategy. We didn't tell them how implicature works. People do figure it out, but it takes time, you know. And so if we'd had them play like 3 games, probably they would have done a lot better. We think the score might have been different. But in the short term, what people really prefer is adaptation. My partner should adapt to me, or I need to adapt to them, one way or the other. And that didn't happen. So it turns out that almost all of our results were negative in this human user study, except for one. We did a Turing test. So we didn't actually tell them whether their opponent or their partner was a human or an AI, but at the end we asked them which they thought it was. And people who are matched with the implicature baseline were 50% more likely to think their partner was human. So that's a little bit short of actually preferring it, which is what our hypothesis said, but it's evidence that at least it is a part of what it means to be human, so we think. So that's a promising result. Still a work in progress. Yeah.
So the AIs, both AIs, when they actually play a card, only played when they were certain or not?
No. If you're using the implicature AI, and I tell you like you have 1 blue card, it would assume that that was a playable card.
Okay, so it is also taking a risk based.
It is taking a risk if you don't have agreement. That's exactly right. And that was, I think, what went wrong here, is that people didn't realize that to start with, and it would just play a card for no apparent reason, you know, from their perspective.
You did the simulation of it. Did you have a team of, and it's a competitive game, so you have 2 teams against each other?
It's a cooperative game, so it would be just 2 players who are on the same team.
So when you did implicature, both partners were implicature, and when you did entropy, both partners.
That's right. It would not be pretty if you put one partnered with the other, because they would come to all sorts of bad conclusions. Yeah. We did not try that, but it might be interesting. Yep. Yes. So there's actually a somewhat thriving community in the AI community, so AAAI and so on, studying Hanabi game theory, basically. So what is the optimal strategy for this? And up until now, it's basically been a fancy version of the entropy baseline. So this is actually a significant step forwards. And this, so for example, the best result before ours was by Osawa, and that was comparable to the baseline performance. I think he got about 19 points or something, and you can see we're getting, what 22-ish. So it is a significant improvement over the significant amount of work that's been done. For fun, later on, you all can look up, there's a paper based on coding theory, which is actually an optimal strategy for playing Hanabi, but it involves essentially very cryptic patterns where if I give you, it's sort of like bridge bidding, I think, conventions. So like if I tell you a yellow hint, it doesn't mean anything about the yellow cards in your hand, but it conveys some other information. And you can actually play a much more optimal game like that, especially if you're playing with 5 players, because then you can give hints to all 4 of your partners at once. But that's a fun thing, but that's very much an aside here. Other questions before I go on? Cool. Okay. So 2 takeaways. Actionable information increases efficiency in collaboration, and adaptability appears to be also really important, and I think something that is worth studying. Okay, so now we get to talk about robots. So these are 2 projects, one past and one ongoing for me, just to give you a sense of what does communication look like in these domains. So the first one has to do with Ikea Bots. So this is about a 5-year-old project now that I did while I was at MIT. These are a fully autonomous distributed furniture assembly system. So these robots are given only CAD files of the parts, and they infer sort of a blueprint of how things should fit together based on the geometry. And then from that, they figure out a plan or a recipe you could think about for what sequence they should be doing things in. So task planning. And then they have controllers that actually implement the tasks on the real robot. Some of them are collaborative, like they're doing handovers or flipping over the table. Some of them are one or the other. And they actually can leverage the fact that they have different tools. So one guy just has a gripper and the other guy has the specialized screwing tool. So it assembles this full table in about 10 minutes, whereas it takes me maybe 5 minutes to build it myself. So not terrible. So it's a cool demo, but you can imagine it doesn't always succeed. Of course, it works in the video, right? Somehow they always work in the video, you know? But they do fail, right? Most people don't come out and say it. The system fails, right? It does. So I wanted to look into how do we recover from these failures when they occur. There's a lot of strategies you could employ. You could retry, you could replan. Sometimes those don't work though, right? Maybe you could just replan repeatedly and it keeps failing every time. Or maybe, for example, a part is out of reach for the robot, so it's just not physically possible. So we'd like a backup plan, which is going to be humans, right? Human-robot interaction. And the way that we detect these failures when they occur is based on our symbolic planner, our task planner, which is very similar to Stroop. So we have a set of actions that are the controllers, essentially, that this robot knows how to use. Each action has pre and post conditions, and the job of the planner is to chain these things together. And we chain them together in such a way that the end result is a table, right? So you can think of this as a contract. The planner is saying, if you do this sequence of actions, starting from this state on the left, you will get a table. But of course, things go wrong. You go to pick up a leg, and then you look at your hand, and it's not there. So something went wrong, right? That triggers a failure resolution process. That in itself, like the question of what remedy do you propose, is a super hard question. Since we were interested here in leveraging human help, we resort primarily to linguistic strategies for asking for help. But in general, you can think about these as resolution symbols, if you will. These symbolic requests are parameterized according to the circumstance of the failure. So that's all the information you have about what went wrong. And you'd like to turn that into a natural language sentence. And commonly this is done with what's called a template baseline. You know, hand the robot the part, right? Fill in the blanks. But often this is ambiguous. Which part? You know, the white leg. Well, there's 4 white legs. Which one do you mean? It can be hard to explain that in a template baseline because it requires more interesting language, like the white leg on the black table, for example. So this is our sort of general context. That's my co-author, Adrian Lee, puzzling over what the robot was trying to say when it said, hand me the white leg. And what it meant to say was, hand me the white leg that is on the table, right? That's a pretty clear, unambiguous sentence. So the question is, how do we figure out that is on the table is really like the right way to say that? That's the question here. You can pick apart these sentences. So for example, the concept of the table as a linguistic phrase is grounded to that physical table in the room, right? There's this correspondence between the two. That's semantics. Likewise, you can ground other parts of the sentence to other objects. The white leg that is on the table is specifically that white leg. And you can also ground actions. So the act of handing a leg to a robot is itself a grounding. And these are things the robot understands, right? It's watching people. It can track objects as they move through the room. This was all done in motion capture, so it's pretty easy to identify things. And we use gammas for the groundings, and so we're basically trying to match up groundings and language. And the normal process you think about here is understanding. So that's forward semantics. And you're asking what groundings best match the language that you heard. And this was solved by Stephanie Telix in her 2011 AAAI paper. And it's the framework that she calls the Generalized Grounding Graph, or G-cubed. And we actually built on that work here. So I want to explain at a very high level what it's doing. There's a lot more detail that I'm glossing over here. But basically, we're, again, trying to search for the groundings that are most likely given the language, right? This is sort of parallel to that generic formulation that we talked about earlier. And the way that looks in practice is that we're trying to ground individual phrases in the sentence and trying to maximize the confidence of the listener. So we could iterate over all the possible objects in the room and ask, is that the table? Fortunately, we have a semantic model which knows which correspondences are likely to be true and which are not, and it says that's very improbable, so we discard it. On the other hand, that one is very likely to be the table, right? And so the model, Stephanie's model, basically factorizes the sentence and factorizes all of these variables into a very tractable representation that we can compute quickly. So she can figure out that that is not the white leg on the table because it fails the sort of on the table check, right? The preposition doesn't satisfy that relation. This, on the other hand, does. So we assign that a high probability. And we do the same thing with actions, right? Driving through the room is a low probability correspondence with a hand me the white leg. So we find the correct action with high probability. Essentially, her model is multiplying all these things together and trying to maximize the confidence of that resulting product. So that's understanding in a nutshell. I encourage you to go and read that paper if you want to know more. The contribution of this work actually is inverse semantics. So we're trying to generate language by asking what language best specifies the groundings, where the groundings are that symbolic help request, right? So we know what robot failed, we know what part it was trying to act on, and that's it. So again, we can start from our framework, specialize it to the language domain. So we're searching for the language that maximizes the groundings. And here we did something incredibly naive. So this is not the smartest way to do it, but it was certainly the most efficient way to start with. So we generated a simple context-free grammar. And using this, we just generated sentences, starting from short sentences and going to longer sentences. And so in our framework, we have a target grounding that we're trying to achieve on the top left. And we have a series of messages that we're generating using our CFG, right? And eventually, one of these messages is going to be output. But before it is, we use the language understanding framework, which is actually trained and pretty good, to try to understand what we just generated. And then we can compare the two and ask, did we say something like what we meant to say, right? And if not, then we just keep going and search for other ones. It's actually a little smarter than what I'm describing. We're using AI search tricks like beam search. But I think there's definitely room for improvement. But the point is really all of the intelligence is in the understanding module, and then we're just inverting that model, right, to achieve generation. And this has the effect, like if you naively invert it, you could just plug in groundings and go backwards to a message. That would be maximizing the confidence of the speaker, which is not what we want. And you get vague things like, please help me. Right? So that's not what we want. But this actually is going to maximize the confidence of the listener, which is exactly what we want, by leveraging the context. So we evaluated this in two ways. First, using Amazon Mechanical Turk, we showed users 5 videos and 1 machine-generated sentence. And we asked them to select the video that is the best response to the sentence. So if the sentence was unambiguous, then people should select the correct video with a high accuracy, right? So we have several baselines that we wanted to compare this against. And since there are 5 videos, chance would be 20% correct response rate. And so help me, as you would expect, people do get about 20% right. We tried this template baseline. It gets about 50%. This is a very domain-specific thing, but Ikea has a lot of identical parts. So there's a lot of symmetry that creates ambiguity. So we got about 50% on the template baseline. On the opposite extreme, I hand-tuned for each query the clearest request I could find on Mechanical Turk, which itself was an interesting process. And we were able to get up to about 94% correct response rate. So pretty good, right? And so the big question is, where does inverse semantics land in here? Well, we got about 2/3 accuracy. So there's about a 30-point gap in there. We know that we could do better. The best explanation I have for this gap is that the language understanding model, which really is a proxy for human understanding, is just not good enough. But the good news here is if there are any NLP people in the room, and if you have a natural language understanding module, you can just plug it into my framework and generation gets better almost for free, right? So really one of the things that's novel about this is the fact that we're unifying the generation and the understanding into a single framework here. We also did a live user study. So this is the baseline, the help me baseline. So in the user study, we gave a distractor task to people and asked them to only help the robot when it asked. So it calls to the user and he comes around and he has no idea, right? He doesn't even know which robot asks for help. But he's persistent. We did give him a few suggestions of how he might assist. And eventually he actually does figure it out. He realizes there's this other robot and he says, oh, I actually don't know which one of you wants help. Do you want this? So he's got it. So this is a success, but it came at a big cost in terms of cognitive disruption, right? So clearly there's room for improvement. So enter inverse semantics. Here the robot asks for help. Please give me the white leg on the black table. And he doesn't run right over and drop everything. He actually finishes what he's doing and then comes around and hands the leg quickly and efficiently to the robot. And then when it's all done, the robot actually says, thank you, I'll take it from here. So sort of saying, we can move on now, right? We're done with this interaction. As you know, it's important to be polite, but we also want the human to know you can get back to work. So I don't have the results here, but as you can imagine just from the video, the inverse semantics did perform quite a bit better for a variety of tests in terms of user satisfaction and so on. So takeaways, inverse semantics achieves generation by inverting a model of language understanding. This is a very general framework. You can generate almost anything this way. But that understanding model really is a proxy for human understanding in this case. And there's clearly a trade-off between concision and clarity, right? You can always try to add detail in order to make a request clearer, but at some point you're actually muddling things further. So you really want the most concise thing that's unambiguous, and that's what you want to say. And finally, you need a source of candidate utterances, which in this case was incredibly naive, but there's a lot of room for improvement. So if you have some educated guesses of what might be good ways to say things, now we can rank them in terms of confidence. Okay, so now I'm going to switch gears and talk about social navigation for a few minutes. Social navigation is a domain that has not gotten a huge amount of attention lately in robotics, but it's actually a very important thing because it is truly a collaboration, right? We have a shared goal, which is to avoid collision while each getting to our destinations. And we have to achieve group consensus without saying a word most of the time. So we're doing this only through very subtle eye gaze, body motion type of signals, right? So prediction turns out to be a really important piece of this because if I don't know what somebody wants, I can't help them get it. So usually we think about the prediction problem as having a path prefix, trying to specify the trajectory, the geometric shape of the path that's to come, right? That I claim, there's been a lot of work doing this, by the way, using a lot of different approaches. Social force, velocity obstacles, a lot of sort of learning and computer vision-based approaches are hot right now. But I claim this is actually solving the wrong problem here. We don't actually need to know the geometry of this trajectory, and we actually don't want to know the geometry. For one thing, the set of possible outcomes is infinite and highly non-uniform. So even if I specify a specific trajectory, that's almost meaningless. Really what you want is a distribution in the infinite dimensional space of function spaces, right? So that gets really messy really quickly. But secondly, people are reactive. So even if you were right, it would change almost instantly when somebody moves and then somebody else reacts and so on. So trying to pin down the geometry of the trajectory is kind of a fool's errand. What we really want to do is separate out the geometry and the topology here. We want to know separately the shape of the path, but also which side are people going to be passing each other on. So the geometry is about the shape of the path, whereas the topology, as I mentioned, is sightedness, primarily in 2D. And when you decouple them in this way, you realize some interesting things. So for example, geometrically, we use path shape to maneuver, to avoid people. We also use it for social signaling, right? So I might do something more abrupt if I want to strongly signal to you. That's changing the shape of my path. The topology, on the other hand, is more about group decision making. So collision avoidance and solving consensus, right? So what that says is that if we can solve these problems on the topological level jointly, that now frees us all up to individually handle these things. And as long as we obey the topology that we agreed upon, you're free to do whatever you want and not worry about what other people are going to do. So you can be reactive without causing these sort of chain reactions that confuse people. So that's our key insight. So we need a geometry and we need a topology. The geometry, you can think about Thurgan and Srinivasa, who looked at this sort of reaching problem for bottles. So trying to signal to an observer, which bottle am I going for? And they discovered that by moving away from the bottle that's not the target, you can send more information about the bottle that is the target, right? So this is a pretty powerful formulation, but it's not complete. So intent in the Thurgan and Srinivasa sense is the destination or the goal. But that's insufficient for navigation because you also have to do collision avoidance, right? So you have to think about, am I going to pass on the right? Am I going to pass on the left, right? So here the intent is both the destination and the topology. That's what we have to agree upon. But that's also what we're trying to communicate, right? So the shape of our path is going to signal information about our topology. And then having agreed upon the topology, we're now free to change the shape of our trajectory as we please. Initially, we're going to have a very high entropy distribution as we're approaching each other. We don't know which side it's going to be on. So we want to use social signals that are going to change that distribution pretty quickly. And we want to classify this, which we do using braid groups from topology. When there's two agents, there's only two ways of passing. And we're used to thinking about this in the XY plane, right? But what braids do is they label these passings as sigma, sigma inverse, project down onto the x-axis while preserving the passing side. And now we look at this in the x-time plane. So over the passage of time, the two trajectories look identical as a braid, except for the order in which they pass, right? It's flipped. So this, as you can imagine, generalizes beyond two agents. We can take n agents moving through a space, look at that in space-time, projected onto the xt plane, and out pops an algebraic braid, right? So on the right, we have our braid string, which is the sequence of sigmas and sigma inverses that tell us the passing order of all of the agents in the scene. So knowing that, that's actually a prediction, right? If we think that this braid is what's going to happen, that's now our contract that everybody can obey, and now we're free to do geometrically whatever we want within that. So when we model braids, what really is happening is there's a set of permutations on the x-axis. There's the initial permutation of how they start. At the top is the goal permutation. And if you're searching over the space of braids, you're essentially asking, how do we get from one permutation to another? Another way of formulating that question is to build what's called a permutahedron, where the nodes are all the different possible permutations of four agents, and an edge connects them if a single swap will achieve that permutation from one state to the other. So any walk that you might find in this graph corresponds to some very complex topological motion of all of the agents collectively in this space, right? So this is now exactly the right tool to reason about this group motion and how things might unfold. So my students, Chris Mavrogiannis, who by the way is about to graduate and might be looking for a postdoc soon, and Valts Blukas, have been working on this problem. So they want to understand intent from the shape of other agents' trajectories. They want to predict others' preferred topological outcome, plan a compatible topology for the robot's own path, and then communicate the robot's intent through its trajectory shape. So just to bring it back to the model that we keep talking about, in this case, the symbol is a braid word, W, and we're going to try to maximize the probability of the braid word given C, which is the path prefix of all of the agents collectively, right? And that would be an understanding problem. The equivalent generation problem would be asking what geometric path shape indicates the preferred topology. So here we're searching for zeta, where zeta is the path of the robot only, right? You don't get to control the paths of all the other agents directly, but as we'll see in a moment, you can actually influence their motions through your choice. So we constructed a machine learning model where we give it the prefixes of all agents for the last 5 time steps and a single robot action, and out pops a prediction of the next 3 passings that are going to occur. So it's a partial braid. But this turns out to be enough for the robot to make principled decisions. And we want to, when we're making this decision, we want to both maximize efficiency in getting to the goal, but also achieve consensus as quickly as possible. And it turns out those two are in conflict to some extent. So here's what we'd call a high entropy, high efficiency approach, which is achieved using velocity obstacles. So everybody just rushes the center, and they're planning in velocity space. So they just find a little hole in velocity space and squeeze into it. And you can see that it is very efficient, but there's a lot of trust here, right? Everybody is trusting that everybody else is running velocity obstacles. If not, then this is going to be a colossal mess. So another approach is social force. This is frequently used for large-scale crowd simulations, but you can see that at a finer scale that robots care about, it's kind of a mess, right? It's not clear how these guys are going to pass each other until the very end. So we would say this is still high entropy, but also low efficiency. So an interesting thing happens when we inject just one of what we're calling our socially competent navigation, SCN, robot with social force agents. And so that's kind of like the adult in the room. So his choices actually affect everybody else's choices. And because it was trained on 1.6 million social force experiments, it knows exactly how those agents behave and can sort of, it's like a shepherd and a sheep, right? So he's learned socially how to control the room and how to get people to move efficiently. So if you have 1.6 million or so videos of people moving, we can train the model the same way. But we think it will work. We just don't have that yet. We are running out of time, so I'm going to skip over the results, but you can trust me, they were good. Little sleight of hand there. But read the paper. It was at IROS this year. So we're using braid strips to abstract away a lot of the uncertainty. That's really the key takeaway here. And we're learning a predictive model of crowd behavior from it. So I want to really get to this closing thought section because I think this is really an important message, which is that this stuff is really important. Thinking about the implicit messages that robots are sending when they do functional effects, this really matters. Because if you do things for purely functional reasons, you are sending random signals to whoever is watching you. So this video comes from Anka Dragan and her legibility work. But you can see here there's a robot running RRT planner. So it's really unclear, like, what is this reach trying to do? And there's a human who's just trying to keep up the best she can, right? That's exactly what we don't want robots doing. And all of your robots are doing this today. I'm sad to say. My robots too. So HRI really requires robots to understand how their actions will appear to humans so that they can be more intent expressive and more actionable as well. So I'm going to show one more video and take remaining questions if there are any. So this is from the same project as Will at the beginning. So here, Julia is asking for the toolbox. But it's heavy, right? What that really means is you need to use both arms. It exceeds the payload limit of one of Baxter's arms. So again, it's basically a regrasp request, but it's disguised as something that a human might actually say. And Baxter is able to correctly interpret that and arrive at a reasonable result here. So with that, I will wrap up. You've been a wonderful audience, and I'd be happy to take questions.
maybe I missed this in the formulation, but it sort of seems like there could be one action which makes two facts extremely likely. And by maximizing the objective you put down, that may seem like a good action. Whereas you're really interested in something like an action which disambiguates between all possible facts as much as possible.
Right, sometimes there are trade-offs. So the circumstance you're describing is the cornuto symbol where, I guess it's that, where you can accidentally, depending on context, you might be implicating one idea or another. There's ambiguity. If you are in a world where that happens a lot and you can't avoid it, then we're forced into Daniel's world where we're thinking about the belief space over each of these facts, right? And to reason in that space, it just blows up. And so usually what people do is one of two things. Either we try to be really unambiguous and make sure there's only one possible best explanation for an action, or if the observer detects that that's